Then Valeria, if it's fine for you, we can start.
Okay, thanks.
Okay. So good afternoon, good morning, good evening, everybody. My name is Michela Meo. I'm from Politecnico di Torino in Italy, and I'm tutorial co-chair of Performance 2021. And so it is my pleasure today to introduce this tutorial and to welcome you all to Performance 2021. So the tutorial that I'm introducing is about a very exciting topic. It's about reinforcement learning for runtime performance management in the cloud and edge. And I think it's extremely interesting because it's putting together on the methodological side a reinforcement learning, which is extremely timely. And on the side of the system, it's talking about cloud and edge. So I think that we are all very interested in hearing your tutorial. So we have three speakers, Francesco Lopresti and Valeria Cardellini, who are associate professors at the University of Rome, Tor Vergata. And then Gabriele Russo, who is a researcher associate and a PhD candidate in the same university. So the three of them, they are very active in the field of distributed computing, performance measurement, modeling, optimization. And so they are really the right expert today for providing a very nice talk. So I don't want to take any more of your time. I leave the floor to our speakers, and I guess Valeria is starting. So thanks a lot, and please enjoy.
Thanks, Michela, for the nice introduction. And here you can find our email addresses. And of course, you can contact us if you have any question also about the tutorial after the ending of the tutorial. So before starting, let's see together some useful information. First of all, the slides of the tutorial will be available after the talk on the performance website. And a second important information, especially for PhD students, is that they may get a certificate for participation. And in this case, to get the certificate, they have to fill out a Google form that you can find here at this link. And we will also put in the chat the link for the Google form. And further communication is about the conference, and it regards an event that will be organized on Friday, which is titled Meet the Star Event, and is an event in which PhD students and postdocs can meet experienced researchers and get comments from them about their work. And in particular, Professor Tassiulias and Professor Srikant will be the stars of the event. And this session will be on Friday at 11 New York City time. So let's now start with our tutorial, and let's start with a motivating example that can introduce us to the challenges that we are going to introduce and hopefully solve, at least partially, with this tutorial. And let's consider an application which can be executed in the cloud or at the edge, or even using some fog nodes. And in particular, this application is a data streaming application whose goal is to provide an analysis of data regarding air pollution. And so you have many sensors that are distributed at the edge of the network in different cities of different countries and in different areas of the cities. And this sensor gather air quality data, for example, humidity, temperature, and particulate matter that can be used to provide an air quality index. And so all this data can be processed and analyzed, for example, to generate some alarms when there is some situation that need attention. And so you can perform the processing on edge devices. You can perform this processing on fog nodes that are located between the edge devices and the fog node and the cloud nodes. Or you can also provide the processing and the analysis using some cloud computing resources. So you can use the full spectrum of computing from the edge to the cloud, and you can provide an analysis that can regard a specific city, for example, Milan, or a larger area, for example, some countries of Europe, as you can see here in the picture. So depending on the area, depending on the amount of data, you can decide to process the analyzing data at different location in this continuum from the sensors to the cloud. But during the processing and analysis, some events that require to reconfigure the application can occur. For example, you can have a specific event that requires a larger data generation from sensors, and so you need more processing resources to process those data. Or it can even occur that some nodes fails during the processing, and so you have to place the components of the application on some other nodes of the environment. So there are, even if we consider this kind of application now, which is not so complex, we can have different sources of uncertainties in cloud and edge environments. In particular, we can have that a working condition can change over time because you can have spikes in the data arrival rates. So you can have a workload which is highly variable or even unpredictable. You can have flapping in the network connections, so you can have unstable network condition, for example, because of traffic congestion. You can have also variable performance of the computing resourcing, the resources you're using for the processing and analysis. And of course, you can have also some security attacks that require to reconfigure in some way the application at runtime. And in addition, you can also have the monetary cost, for example, for the cloud resources that may change over time because, for example, you're using spot instances whose price vary over the day. In addition, other sources of uncertainties that we can have in cloud and edge environments include heterogeneous computing and network resources, because you can have high-end servers and you can have low-end servers, for example, Arduino devices. Then you have a application where in which you have black box specification. For example, you have service level agreements that regard the latency time of the entire application, and you don't know the latency that is due to a specific component of your application. In addition, you can have uncertainties regarding the performance models you can use to define a model to use of your application and the environments in which the system and the application operate. And of course, an important source of uncertainty is related to the presence of humans in the loop. So given this uncertain situation now, we have many problems that can arise during the working of our application. Our question is, how can we design automated performance management solution that are able to cope with uncertainty and are able to mitigate uncertainties? And so a first answer to this question is to follow an architecture-based approach and to organize the system as a self-adaptive system that has the so-called self-star properties. So in general, a self-adaptive system is a system that can handle uncertainty in its environment, can handle uncertainty about itself, and uncertainty also regarding the environment, and can manage autonomously its goal, in particular its performance goal, without requiring human interface at all, or with a minimal human interference. So in this context, we would like to have a system that has the so-called self-start property. So for example, a system that is able to self-optimize itself, that is able to self-heal to survive from and recover from failures. And you would like to have a system that is able to reconfigure and also to self-protect from, for example, security attacks. So when we want to organize the architecture of such a self-adaptive system, usually we introduce some monitoring components. So we have some sensor from the environments, and we have some monitor instrumentation regarding the system that we want to control. And in this way, providing the monitoring input to the managing system, we are able to control our managed system and mitigate the uncertainty that we can have from the environment. And a very nice introduction to self-adaptive system is provided by this recent book by Professor Danny Waynes. So coming to the tutorial, and so to the goals of our tutorial, our goal is to present you with a collection of techniques that are centered about the idea of learning how to make optimal decisions through the interaction with the managed system. And in particular, we are going to apply these learning techniques to manage in an autonomous way at runtime the performance of applications that run in edge and cloud environments. And in particular, we will explore reinforcement learning solution to support self-adaptation. And our focus during the tutorial will be on a specific concern, so on a specific task that allow us to optimize at runtime the application, which is the auto scaling. That means that we can scale out or scale in the number of replicas that each component of our application is using. And we will focus, as I already said, on a particular application domain, which is, of course, related to cloud and edge application. So coming to reinforcement learning is a subset of machine learning, which in its turn is a field of artificial intelligence that deals with models and methods that allow machines to learn from data. Here you can see three different branches of machine learning. That means supervised learning, reinforcement learning, and unsupervised learning. In a nutshell, with supervised learning, the system can learn from a training set of labeled data that are provided by an external supervisor. With unsupervised learning, the system can find a structure which is hidden in a collection of data that are unlabeled, so you don't have an external supervisor. And with reinforcement learning, the system can learn through trial and error interaction with the dynamic environment. And the basic idea of reinforcement learning is to have a reinforcement learning agent that dynamically interacts with the environment and receive from the environment some feedback in the form of a reward. And the goal of the reinforcement learning agent is to learn how to act so that it can maximize a long-term reward, what is called an expected cumulative reward. So the process of learning is a sequential decision-making, and the learning is based on the observed samples of the outcome. And the learning is based on a trial and error experience. That means there is no complete knowledge of the environment a priori, and in particular, there could be no knowledge at all. So you can think about this learning process as, for example, a child that learns how to walk. And with trial and error experience, the child can learn how to stand up and how to walk without falling down. And we don't have time to explore different application domains where you can use reinforcement learning. But for example, you can find some nice videos on the introductory lesson by David Silver. If you look for his course on reinforcement learning. And so during this tutorial, we will deal with some issues, some basic and some more advanced issues that we can face during the learning process. First of all, we will consider a fundamental dilemma, which is the trade-off between exploitation and exploration. So exploration means that you learn more about the environment, and exploitation means that you follow the reinforcement learning agent follows the most promising strategy using the experience it has gathered so far. And so, of course, you have to trade off between exploitation versus exploration, because if you only exploit, you may lose some good action that you don't have seen before in the past. On the other hand, you cannot only explore, because exploring you can follow some bad actions, and so you can have a negative reward. I forgot to mention that in the modeling framework that you will that will be introduced later by Francesco, we will use rather than the maximization of the reward, the minimization of cost. And so we will use cost rather than reward, because our goal in this case is to minimize the long-term cost of the actions. Another issues that we will deal with during the tutorial is the use of model-free and model-based approaches. With model-free approaches, you don't have any model regarding the environment. And so the reinforcement learning agent only learns from experience. On the other hand, with model-based approaches, you use a partial knowledge of the system to drive in some way the exploration actions. And so we will first see later some model-free approaches, and then we will focus on model-based approaches. Then another issue that we will deal with during the tutorial is how to handle multiple objectives, because we will see that we will have different objectives that can also be conflicting between them. Another important issue we will consider is how to address some performance related issues. In particular, we will see how we can reduce the occupancies of memory, and how we can improve the speed of convergence of the learning process. In addition, we will see how we can increase the scalability of the learning process, so that we can handle large state sizes. So when you have a large space. So in particular, in the first part of the tutorial, which is presented by myself, beside this introduction, we will see some basic architectures to deal with the deployment of self-adaptive application. Then my colleague Francesco will present a brief introduction to Markovian decision process, and then he will deal with methods for tabular reinforcement learning, where you have a small space of states and actions. And then my colleague Gabriele will introduce you to more advanced techniques that you can use to deal with large state space. So going into the detail of the self-adaptive application deployment, we have already seen an example of a CloudEdge application, and we have it's easy to realize that we have a multitude of different and possible applications in different domains. The application that we have can have different quality of service requirements. For example, you can have latency sensitive application in an edge environment, or you can have applications that demand for a high throughput. You can have applications that differ for the size of the deployment, for the number of components of the application that are involved. For example, Netflix has distributed architecture application based on the microservice architecture, which are composed by almost 1,000 of different components. And you have many other sources of differences. For example, the technology you use, the programming language to develop the application, and so on. In our tutorial, we will consider two specific types of distributed applications that are deployed in cloud and edge environments. And in particular, we will consider data stream processing application and microservice-based application. They have in common a structure which is based on a workflow, as you can see here from two different examples. And the workflow defines the dependencies that you have between the application components. And usually the workflow of this application can be modeled as a directed acyclic graph. The application in this case that you can see on the top is an application related to it's a data stream processing application where you have a sequence of components that are called in this case operators, and you have a continuous stream of data that flow through the components, and each component or operator applies some specific function. Now, for example, you have here a parsing, and here you have an operator that performs a partial rank. This is an example of a workflow that is related to the processing of a data set regarding the New York City taxis. And the goal in this case is to find out the rank of the most convenient areas of the city of New York for taxi drivers. In the second picture, we can see on this slide, we have an example of a microservice-based application, and this is the application used by Google to demonstrate the Kubernetes functionalities. And in this case, we have an online boutique. So the user can shop browsing a catalog, can receive some recommendation about products, can decide to buy a given product, and so can finalize the payment and the shipping of the product he or she has decided to buy. And the components of both kinds of application can be stateless. That means you don't have any state associated to the component, and stateless component are easier to manage, or the component can be stateful. That means you have a state associated to the component. So when we talk about the deployment of CloudEdge application, first control knob that we can consider is how to place the application components on the underlying infrastructure. And so we have typically an initial placement, and then we can adapt a runtime displacement during the operation of the application, so to improve it. But in our tutorial, we will not focus on placement, only marginally, and we will rather focus on the elasticity of application. That means how to scale the application. Elasticity is a key feature of cloud native and edge application, and the idea is to adapt to workload changes by provisioning resources in an autonomous manner without having interaction with the user or the administrator of the application. We can employ elasticity at different levels, in particular at the infrastructure or at the application layer, and we will focus on elasticity at the application layer. When we scale application, we can decide to scale the application and its components considering two dimensions. In particular, we can consider vertical and horizontal scaling. Horizontal scaling means that we scale out, that means we increase the number of replica, or we scale in, that means we reduce the number of replica for each application component. In this way, we can exploit multiple resources, for example, multiple cores or multiple nodes. But when we scale out or scale in a component, we can have a reconfiguration overhead, in particular if the component is a stateful one. We can also consider another direction of elasticity, which is vertical scaling. In this case, we can scale up or we can scale out the amount of resources which is assigned to each application component. In this case, the scaling overhead can be reduced, but it depends on specific framework, as we will see in a few minutes with Kubernetes. The cons is that usually you have a limited scale-up capacity because it depends, of course, on the amount of resources that you have available, for example, on the physical or on the virtualized node on which you run your component. So when we consider elasticity, and you will see it when considering the cost modeling with Francesco and Gabriele later, you have to take in account the cost that you can pay because of scaling decision. For example, you want to use elasticity because you want to reduce the violation of performance requirements that can be specified in a service level agreement. So in this case, you would like to use more replicas of the resources, so to reduce the risk of having some performance penalties. When you scale out, for example, you have to consider also a cost that you pay because of the reconfiguration of a RED. It depends on the implementation and it depends on the kind of elasticity, horizontal or vertical, but it also depends on the kind of component, because it is much more expensive to scale out a stateful component because you have to repartition the state rather than scaling out a stateless component. In addition, you have to consider also the cost that is related to the resource usage. And this cost depends not only on the amount of the resources you're using, but also on the type of resources you want to use to scale your application. And so you can see these easily that these objectives can be conflicting, and you will see how the reinforcement learning agents can learn also to trade off among them. So to conclude my part, let's go a little bit into the detail of the architectures of self-adaptive systems. And let's introduce to this purpose the reference architectures for self-adaptive systems, which was introduced by Kephart and Cass in their seminal paper about autonomic computing. I think you have already heard about this reference architecture, which is called MAPE. That means monitor, analyze, plan, and execute. Sometimes this reference architecture is also referred to as MAPE-K because we include in the acronym also the shared knowledge that can be used. And so the monitor component is related to collecting data from the system, from the managed system and the environment, and through sensor, pass this data to an analyze component that can observe and analyze situation and can determine in this way the need for adaptation. The next component in the loop, of course, this is an autonomic loop, is the plan component that you can use to define the actions that to adapt the managed system. And finally, you have the execute component that is in charge to enact the plan and to adapt the managed system through effectors. And as I said before, you can have a shared knowledge that keep relevant information about the managed system, the environment, and performance management goals. So this reference architecture has been investigated a lot in the past. There are many solutions that regards the monitor and the analyze, and you have various design options that you can consider, but I will skip them because our focus is on the plan phase, because in our tutorial we want to use reinforcement learning as a methodology to manage at runtime the performance of application. Of course, reinforcement learning is not the only methodology that you can use. You have here a list of approaches that have been used in the past, and here you can find some references to surveys that review these different approaches according to the domain, for example, data stream processing application, according to the concern, for example, elasticity, which is our focus regarding the deployment. And also, there are two recent surveys regarding the use of machine learning approaches for all the phases, in particular the monitor, analyze, and plan phases of the MAPE loop. But let's consider, as an example, a scaling policy which is usually implemented in most frameworks, for example, in Kubernetes, or in the auto-scaling service provided by Amazon Cloud Service. This is the so-called threshold-based policy, where you define high and low thresholds on some metrics, for example, the CPU utilization, the memory utilization, or the response time. So you can have both system-oriented metric or user-oriented metrics. And the idea of this basic policy is that you compare the policy compares these measured metrics against thresholds and change the replica numbers if the thresholds are exceeded. This policy can be reactive or proactive. In case of a proactive policy, it needs that you use predicted metrics rather than measured ones. And here you can find an examples of rules of a dynamic scaling policy, which is used by Amazon in the auto-scaling service that allows to scale virtual machine instances. So, for example, if the utilization level of the CPUs of all the replica is higher than 70% in the last minutes, then the controller adds one new replica. This is a quite simple and intuitive policy, but it's not so easy to use in an effective manner, because the main issue is how to define the threshold, because it can be subjective, it can depend on the application and on the specific application components, because you can have different components that, for example, are CPU intensive or memory intensive. And so the overall behavior of this policy is prone to uncertainty. Let's now consider how we can design the architecture of the managing system. And in particular, let's consider how we can distribute the different phases of the MAPE reference architecture among the components of the controller system. Of course, the first solution that we can consider is to have a centralized MAPE where all MAPE components are on the same node. Of course, this solution is the simplest, because in this case, the controller has a global view on the system. But if you consider cloud, and in particular multi-cloud and edge environments, this architectural solution lacks of scalability and resilience. So we can consider how to decentralize the architecture of our controller, of our managing system, and we can use different patterns, and you can find a nice survey regarding the different patterns you can use in this book chapter. There is no clear winner among all the different patterns you can use, because it depends on the application, on the environment, on the features and requirements of your application. But we will consider in this tutorial 3 different patterns. The first one is the so-called master worker pattern, where you distribute only the monitoring and execute component of the make phase. So you keep the analyze and planning component centralized on the master. In this way, the master has a global view, but you have a communication overhead, and of course, you have a bottleneck risk and single point of failure on the master of the where we have the analyze and plan phase. At the opposite of the spectrum of decentralization, you can have a fully decentralized solution where you have multiple control loops, and each control loop is in charge of some part of the controlled system. And for example, in cloud and edge application, you can have a distinct control loop for each application component. This solution in particular improves scalability with respect to the master worker pattern that we have seen in the previous slides, but it becomes more difficult to take joint adaptation decision. And of course, you can realize this fully decentralized pattern in different ways, because you can have a different degree of interaction between the different components that are of the MAPE loop that are distributed on the different nodes. You can have also have the case of no interaction at all between the different decentralized nodes. A solution that we also consider in this tutorial is a decentralized hierarchical pattern, where you have multiple MAPE loops, and each loop can operate at different time scales, and can be in charge of different concerns regarding the application. In particular, the top level MAPE loop can achieve global goals and can have a global view of the entire application, while the bottom level MAPE loop can control, for example, in our case, a single component of the application. And for example, we have used this hierarchical pattern to extend the architecture of Apache Storm, which is a framework in the context of data stream processing, to control the elasticity of data stream processing application. And you will see in some minutes with Francesco the planning policies that we use and that are based on reinforcement learning. To conclude, let's just consider a framework, a real and popular framework, where you can include, where you can implement some of the techniques based on reinforcement learning to scale, to provide elasticity. And the kind of framework we consider is Kubernetes, which is a well-known and the most popular platform for container orchestration. And Kubernetes can handle the scaling of a containerized application that are deployed using Kubernetes. And in particular, here you can see the architecture of Kubernetes. I'm not going into detail. It's a master worker architecture. And in the worker nodes, you can see that you have different pods. Here we have a single node where you have a single multiple pods, and a pod is a group of one or more application container, for example, Docker. And so multiple pods can run on a worker node. And Kubernetes provides some auto-scaling features at different granularity level. For example, you have auto-scaling at the cluster level. That means Kubernetes can automatically adjust the size of the Kubernetes cluster. That means the number of worker nodes that you have in the system. And then you have auto-scaling at pod granularity. That means you can scale out or in or up and down the pod that you have inside each worker node. And for example, there is a vertical pod autoscaler that allows Kubernetes to scale the amount of pod resources. And in this case, it's a heuristic policy that is implemented, which is based on the historical resource usage of pods. But in this case, just to recall what I said before, if you consider the cost of elasticity, in this case, you have a reconfiguration of a RAID, because each time you scale up a pod, Kubernetes restarts that pod. So you have a time required to have a new pod up and running. The other autoscaling at pod granularity that we have in Kubernetes is the horizontal pod autoscaler. In this case, Kubernetes can scale the number of pods. And in this case, the policy is based on CPU utilization or some other metrics that you can gather from the metric server of Kubernetes. And the policy which is used by Kubernetes is a simple heuristic policy, which is a variant of the threshold-based policy that we have seen before. If you analyze this policy, you can notice a trick that has been used to mitigate some fluctuation that you can have in the replica number that depends on the fluctuation that you can have in the metrics that are used to decide about the scaling. And in particular, we have customized the scaling and also the placement of Kubernetes in a framework that we have called Gcube, which is an extension of Kubernetes, where we have introduced auto-scaling policies based on reinforcement learning. And we have also provided network-aware placement in such a way to deal with geographically distributed worker nodes. And here you can see that we have implemented the reinforcement learning policies that you will see in some minutes inside this newly added component that we have called the replication manager. So that's all for my part. I forgot to mention at the beginning that you can write questions on Slack. And now we can have a 5-minute break before the second part of the tutorial, and I will be available on Slack or on the chat if there is any question about this first part. Thanks, bye.
Okay, this is Francesco for the second part, but we thought that between the switching and the context, it's worthwhile to take 5 minutes break. So if you don't mind. Is Michela is around?
Yes, I think it's fine. Yeah.
It's okay, fine. I don't know. I
Yeah.
don't find the mute button, so I will avoid say bad things about.
Yeah, no problem. Yeah, I think 5 minutes is really
It's
okay.
okay.
Thank you.
But we will like 5 minutes sharp start.
Yeah, sure.
Ready for the second part? So
Yeah, that's perfect, Francesco. You can go on.
you can go? Okay, perfect. Okay, then in this second part, we will, first of all, thanks Valeria for setting the stage for the tutorial. Now I will discuss the reinforcement learning edge setting. So we'll go in the gory details on how you can use reinforcement learning for management of resource in the edge. The necessary background material on Markov digital process, which will help us to understand the notion of reward and dynamic system properly. Then we go with my part on the tabular techniques on reinforcement learning, which are the easy part, which is basically the Q-learning, the most well-known of policy reinforcement learning algorithm, and then the model-based. Then we will discuss some more advanced topic on tabular technique, which is the use of post-decision state, which can be easily summarized to how to take advantage of partial knowledge on a system. As we see, when we get to the larger system, we end up with very large state space. In this case, we cannot resort to the tabular techniques. In this case, we resort to value function approximation, and there are different approaches. The basic one are what are known as linear approach, and the easiest implementation is tying, and the nonlinear function approximation that end up dealing with a neural network and with deep Q network. The second part is the one presented that will be presented later by Gabriele. So most of this basic material is inspired and borrow the basic concepts from David Silver tutorial and classes on the very same subject. So Valeria has described as the different architecture alternatives for our system. We can have a centralized controller which oversees the operation of the entire system, or we can simply, in a very different approach, have a distributed controller, each overseeing each component independent from one another, and there are pros and cons on the different solution. Sometimes we have solutions that lie in between, where we have a decentralized controller plus a hierarchical component that oversees the operation of the single controller. So our starting point will be with the component elasticity of a single component, which can be very simple problem, but we will see that it easily gets very complex when we deal with heterogeneous resource or heterogeneous environments. So even if the system can look very limited, we are looking at the single component for now, it can be seen just a simple version of the centralized controller part, and we will be using it as a running example throughout the entire rest of the tutorial, giving hint on how things change when we deal with the larger system. In our setting, what is this single component? We have a single component running possibly multiple replicas. It gets data upstream from some other component of the application, and downstream we have another component which receives the output. The single component is managed by MIP system itself, so we see the monitor, the execution component, and possibly remotely the analyze and planning part. And this is something that is actually managed using very simple policies, given the complexity of the application, which are based, as Valeria has just told us before, on using a threshold-based policy. Basically, we can monitor the component utilization. If utilization goes up a given threshold, we add new replica to the system. If utilization goes too low, since I'm paying for the resource I'm using, I shut down one or more replica and I get less component. And I do this dynamically. So the idea in our setting is that we would like the scaling manager not using a threshold, because threshold gives us a very little control on what is actually happening. We would like to have key performance indicators to monitor and to account for the amount of allocated resource, because basically I end up paying amount according to how much resource I'm using. Then the second thing we care about is performance. Typically, we care about what is the response time of my component. And then the reconfiguration cost. As we just saw before, when we change the number of replicas, we need to reconfigure the entire component, which can take significant time. If I don't properly configure it, I end up wasting so much time changing the system multiplicity that is not worth the cost and the downtime I have to incur in doing it. And we set this as a reinforcement learning problem. So in our setting, the agent, which is the reinforcement learning parallel, is the one who takes decision and oversees the system, is our scaling manager. And the environment, which is control, is the application component. And in a more general setting, it includes the application itself, but also the underlying software and hardware infrastructure. And the idea of reinforcement learning is we would like to learn the optimal policy through interaction and feedback with the environment. It is because we don't know actually how the system is, but also because the system can be subject to evolution over time, because other components are interfering with our software, because some condition change, because the response time of the component depends on actually it is implemented in which language. It depends if it is run on a virtual machine, on hardware, a different setting. And before getting into detail, just a rough idea what makes a reinforcement learning agent. It is characterized by policy, which basically it describes how the agent behaves. And a value function, which is its own measure on how good each state or each action is. And then a model, which basically is how the environment is perceived or represented by the agent itself. For doing this, we have then the policy, which is the agent behavior. Simply put, it is a function that associates to a given state an action. If the system is in a given state, I do this. If it is in another state, I do something else, which is the basic policy. For example, the threshold policy is when utilization is low, I do nothing. If utilization is too high, I add a replica. If the utilization is too low, I remove a replica. but possibly we can do something more sophisticated than that. The deterministic policy, given a state, it perform a particular action. We can have in general, but we will not get into this stochastic policy where we have a distribution of possible action given a state. So in the simplest possible implementation, I have just a table. Every system state, what I'm supposed to do, what the agent is going to do. The second part is the value function, which is a measure of how good is a given state or a given state action combination. This is a possible representation of the value function of our system. I have multiple state, multiple system configuration, multiple action choices, which can also include basically I do nothing, and what is the expected cost of taking that decision. As Valeria anticipated, we will look at cost rather than revenue. So we always try to minimize something rather than to optimize something. So I apologize in advance if I will speak of maximizing something. In this setting today, we want to minimize costs. And the last part is a model of the system, which basically is the representation of the system by the agent. It can include a model that predicts what is the next state. If I am on a given state S and I do A, what happened to my system? It will change. And then at the cost. If in a given state, I do some particular action, what is the immediate cost I will pay for doing this? So, given this, I move slightly to talk about the general setting, which provides the necessary background to dealing with reinforcement learning. Since this tutorial has been thought for PhD students, I don't know which is the relative background, so I will spend, I hope, no more than 5-10 minutes of giving some background on Markov decision process, which is the reference background, and also it gives us a way to completely describe the system under study. So I apologize in advance if it can be too brief, but the time allotted for dealing with the more interesting topic required this as a necessary background. So a Markov decision process is a tuple of a finite state of states as a finite state of action. Action in our setting can be just add a replica, do nothing, remove a replica, and the state is the system configuration. Then P is the state transition probability, the probability that the system being in a given instant, in a given state, doing some action, how the state is likely to change in another configuration. And then the cost associated to doing a given action. Now in the literature, you have the state, the cost be associated to state action pair. Sometimes, and also we will need it, we need also to define the cost associated to state action and next state. The two are related. Knowing the transition probability, I can compute the latter, the former knowing the latter. And typically, we're not interested to the actual value of each possible occurrence, but we are interested on the average, so on the expectation. And then a discount factor that we will see soon how the role it plays. Now, we are dealing with Markov system because they enjoy some nice property. So I apologize for these commas which should not be there. A system is Markovian when its future as function of its past depends only on the current state. So basically, the future is independent of the past given the present, say it shortly, which is a very nice property we will take advantage in when dealing with Markovian system, which basically means that the current state captures all the relevant information of the history in the current state information, or more formally, the state is sufficient statistics of the future. A policy in this setting is the same as I said before for reinforcement learning, is a distribution over action given a state. So in a more general setting, on a given state, I have a probability of taking some particular action. in the deterministic case, which is the one we will talk about today, an action is just a function of a state. I am in a particular state, I do some particular action. A policy defines how the agent behaves. So it is this is the final outcome of our work. And in MDP, the policy depends only on the current state, which need to be properly defined. So in MDP setting, which is the objective, is not studying a particular policy, but finding the optimal policy. That means the policy or the policies which minimize the expected cumulative discounted cost. So I'm not interested on the cost on a given instant, but I take the cost over the entire time horizon I'm considering, and often we consider infinite horizon, and where I sum up the cost I incur at every step and discount the future cost by factor gamma, which basically tells how much I care about the future cost. And to set the stage, we need to define how we want to compute the relevance or the goodness of a given policy. We need to add some additional information. This is summarized by the value function. First, the action value function, which is used universally with capital Q on a given state, a given action, is the expected cost starting from a given state and taking an action and then following a policy. So the idea is that I'm using a policy pi, and I wonder what is my expected cost if in a given state S I take action A and then I keep going with the policy I have using. More general, I can also care about the state value function, which is the expected cost on starting at a given state and from this state using the policy. So the difference in one case, I'm using action A and then following the policy, and instead when I look at the state value function, I follow the policy from S from now onward. The two functions are related, and in particular, in our case, we'll see how it boils down. So this expression have a nice property which leads us out. We can compute basically the optimal policy, which is the ultimate goal when we solve MDP. And basically the idea is, let's first write the action value cost, which we have given before. So this GT, which is the discounted cost over time. And the idea that if we can write it down, we can see it comprises two different components. So let's start from scratch. This is basically the definition. Then the other things is I write GT as the sum of discounted cost over time. So I have the entire series. Remember, since it is the action value function, it is given the starting state and the starting action. If I factor out gamma, then CT1 plus gamma CT2, etc., is just the expected cost from the next state onward, which basically allows me, if I write the expectation, to write this equation, which holds for every policy. So basically, the expected cost starting in state S and taking action A is equal to the expected cost of taking action A in state S plus gamma, and then the expected cost of the future, which depends on the transition probability, what is the next state given the current state and the action I take, and what is the action value function of the next state onward. And onward, I just follow the given policy. So this gives us this nice recurrence equation. I can do the same with the value function, so I just write down the equation for your convenience, but it follows the same argument. Now, why I care about this? Because we are not interested on generic policy, which can be interesting by itself. We are interested on the optimal policy. So basically, I want to find the policy which in our setting are those that minimize the Q function and the value function. So it is the minimum all over the possible policies. And the value function equally. So what is nice that for this type of system, for the optimal policies, which I differentiate rather than writing QPy, I'm writing here Q star, we have the well-known Bellman equation, which basically the main difference in the equation, this is the difference from generic policy to the optimal policy, here I have the minimum. So basically the optimal cost starting in S and taking action A is given by the average cost on S of doing action A plus the discounting cost of doing the best action from now onward. And basically this can be written using just the Q function or a combination of Q and the value function. And I focus then on the second because on the implementation it's often convenient to use the second rather than the former. So what is nice about the Bellman equation is that if I can get the optimal policy, I can get the optimal policy, sorry, giving the optimal value action value function. How? But if I have the optimal action value function and I have to decide what to do, I basically take the action which minimize my Q function. This provides the best action, and this is denoted as P star S, which is the action which provided me the best performance. And just to give an example, assume this is my Q star SA for a given system. I have 7 states, 3 possible actions, and I have to wonder on each state what I should do. Since I want to minimize my cost, it is obvious that in state 1, I should take action free. In state 2, I should take action free, and so on for the other, which basically tells me what is the optimal action given the state. So basically the question when we try to solve MDP is how can I compute the optimal Q function, so the Q star function, from which I directly derive which is the optimal policy. This is not very difficult. This is a well-known result, and it can be computed using different algorithms. The one we will use, because this is the one we will use also in reinforcement learning, are based on the value iteration algorithm, which basically look at the Bellman equation as a way to iterate the Q function from some initial value to the optimal policy. Basic the idea, let's look at the right member and assume we know for the possible successor state S prime, the optimal Q star S prime A prime for every combination. If we know this value and I know this probability and the cost, I can then compute the Q star for a given state S pair. So basically, rather than see this as an equation, I see this as an assignment. And the idea that this assignment can be the base of iterating over the Q value and found the optimal. And this is basically to apply these updates iteratively, starting from some initial guess. And it works because the contraction mapping theorem guarantees us that this algorithm basically works. And this is basically what is the value iteration, which is my final part on this very short MDP introduction. Basically, I initialize my QSA function for E equal to 0 for every state and every action. And then I repeat for every state and every action the equation we just wrote, which basically is looking the Bellman equation as an assignment operator. I iterate until the difference between two iteration distance becomes smaller than a given tolerance factor epsilon. When I'm done, I have the optimal Q values from which then I get the optimal policy. So this is very simple and well-known algorithm which sets the stage for everything we'll do from now on. There are different ways to write it. The former, I have everything written with respect to the Q values. The second, sometimes it's more convenient. I have both the Q and the value function of y. Algorithmically, it's more convenient to use the second version because I don't have to compute minimum here on every iteration, but this is just detail. It's just two different ways to write the same algorithm. So this is just background material, but for the self-containment of the tutorial was necessary. Now let's go back to our real system and let's look how to deal with horizontal scaling and use MDP formulation for this problem. And in this setting, now we have to get some detail. That's why we wanted to use a very simple setting, because things can get very complex even in this simple setting. So we have to decide which is the state of the system. So in a very simple case, which means homogeneous system, I have the system state is given simple by the component parallelism. How many parallel component I have running for a given specific component, application component. So sorry, how many replica I'm using for a single component, ki, which runs from 1 to a maximum number. So here, for example, is 2. The other component of the state is the arrival state, which is the number of input tuple per second are arriving at my system and I need to process. Then for every state, I have to define what is my action. So it can be very complex, but in its simplest form, I can assume I can do nothing. I just don't change my replica and number of my in my component. I can add another replica, so I can serve better the incoming input, or I can decrease the number of replicas because I have too few arrival over time, and I don't want to waste resources. So the given state here is indicated. There are some just little detail to care about to be consistent. If we have a discrete time, which we use to model our system, but every actual system is over time is continuous. So we define time E, the interval between the time I and time I plus 1. We define as K1 the number of running replicas of a given component at the start of the given instant. We define as the arrival rate as the arrival rate over the last interval. This is because only at the end of an interval I have an idea of what is the arrival rate, and so I have an idea of the past but not of the future, and I have to decide what I should do next. Given the current number of replicas and what has been my last interval arrival rate, which I both use sub I to denote the two of them, I have to decide what to do. I can do nothing, so keep the same number of replicas, add the replica, or remove a replica. So in this setting, the state of the system is just this, the pair k, number of replicas, and lambda is the arrival. Since we want to keep things simple, we discretize lambda given a quantization step size. So we have a discretized state space, which is the number of replicas, and a discretized version of the arrival rate. We discretize up to L at different values, going from 0 to a given maximum, depending which is the reasonable range of arrival I have to, I'm supposed to see during the interval. And then the action. So what is nice, and this is relevant for this running sample, is that the transition probability, which means given the current number of replica and the arrival rate and the action, what is the next number of replicas and next arrival rate. And if we write it down, we have clearly a dichotomy that given our action, the impact on the system, we have something that is rather obvious. If I add a replica, the number of replicas will increase. If I remove a replica, the number of replicas will decrease by 1. So it's very obvious what is the impact of action. But then there's something which I have no control on, which is the arrival rate. What happened to the arrival rate, I have no actual control. So in this very simple case, the transition probability has a nice form, which is the transition probability of the arrival rate, which I have no control of, and the impact of my decision, which is deterministic. If I remove a replica, I know exactly what is going to happen. This is something we will come back soon, because this impact when we have to do the learning, the fact that there are things that are obvious in our system and things that are not. To define a policy, we need to introduce which is our cost model. As Valeria introduced before, in our cost model, we have to take care of what are the relevance factors in our system. And in our cases, we've seen that we have a combination of things that we have to care about. One is the resource cost, one is performance, and the other is the reconfiguration cost. Since there are multiple of them, the simple way to deal with them is using simple additive weighting method, which basically build up the cost function having a weighted sum of the different costs. Here we took a very simple approach where each cost is a number between 0 and 1, which sum to 1. So the maximum of the weight is always 1. And then each component of the cost is normalized itself between 0 and 1. So here we have the fraction of resource I'm using, assuming Kmax is the maximum. Then the second component is if I'm or not exceeding a given threshold. Since I want to have some measure of how the performance of the system is doing, I can have typically what we have been using, for example, an important performance index is the response time, and we were measuring whether we are respecting the service level objective. So we are measuring either we are exceeding or not the maximum response time. So we are basically counting if we have performance violation. And then the last component is a 0-1 cost. 0 if we do nothing, 1 if I remove or add a replica. So by playing around with the weight, we can have different cost functions which impact the different overall discounted cost. And when we compute the optimal policy, we end up with different behavior. Just to give an idea of what happened on this being run on simulation, so it's simpler than the gory details of the actual system, we have the daily input rate arriving to a given operator, and they are the same over the three figures. Then we run value iteration using different weight. So in the first case, we put 60% of the weight on performance and 20% of the weight on resource and reconfiguration cost. In the second picture, we look at the reconfiguration cost being the 60%. So we don't want to reconfigure as much as possible. In the third case, we put more attention to the amount of resource I'm using. So 60% to the amount of resource I'm using. And these are just three possible numbers. If we play around with different weight configuration, we get completely different performance. So just to give an idea of what happened in this case, in the first example, I care about performance and less about the rest. I end up having a system which have very few violations over time. It has a reasonable number of reconfiguration would basically follow the input arrival rate surge and a rapid decrease. If we look instead to not reconfigure too much, then actually something which is very different, which is basically it try to end up using more resource on average, just because the system wants to be sloppy, it doesn't want to get too many reconfiguration. We have higher number of violations, less reconfiguration, and more resource consumption. But if I care about the resource, basically I am on a low budget. I don't want to use too much resource, but I care somehow about performance and reconfiguration. I end up having much less resource usage over time. I end up reconfiguring many times and having a lot of service agreement violation. So it really depends what we put our attention on, we get very different performance. Now, this was a very simple system. What I like to stress that the simple system can be changed with little modification. For example, the previous model was looking at horizontal scaling, which basically I changed the number of replica of a given component, but there is also the possibility of doing vertical scaling, which basically is having the same component but adding resources to it, like a CPU share and memory. So we can change slightly our system rather than having number of replicas and input rate is number of replicas, number of resources allocated to each replica and arrival rate, and changing the action we play around rather than just adding, removing something is also downsizing or upsizing my resource. I can have a simple action space, or can have a more elaborate where I can add and change sides jointly. And we get different performance on the same system. The model is basically the same, it's just get more complicated the overall analysis and computation time. So probably I spent too much time on this material, so I apologize for this, but this provides us the background modeling on of our problem. Now, moving to the reinforcement learning side is a completely different problem just because the system is actually the same, but I have an idea about how the system really works. I know probably no transition probability. I have an idea of the cost I'm incurring. In this case, we want to use another approach where this is where reinforcement learning comes into play. And the idea of all reinforcement learning technique to the very bone is this. I initialize the Q function at the beginning. I start running the system. So sorry. Something I'm told before that when using value iteration, if I have the model, I solve the model offline, I start my application, and I already know what I should do. But if I have no model of the system, using reinforcement learning, I have to learn from scratch how the system behaves, and learn by doing. I have to understand what I should do. So the MDP solution applies only if I have a model of the system before starting the system and solving the system beforehand. Here I'm running the system, so if you see the big difference, now the index is not more I, it's not more an index of loop I'm solving. I'm running the system over time, and I'm looking at different time instant. So I initialize the Q function, and then basically, since the system is already running, I don't have time to learn without doing. I choose a scaling action, basically on what I already know about my system, and we assume that what we know are the estimates of the Q function. Then I observe what happened, I observe which is the cost I pay, I observe which is the next state, and update my Q function accordingly, and then I see what happened on the next iteration. So I learn little by running the system. So from now on, we will use color code the different parts to see what change between the different algorithms. In green, we will have the scaling action. In pink, the observed part. And then sorry, I get something wrong with the color coding. It's not important. So in the red, the update part, in the blue, the observation. So there are many ways to do reinforcement learning. We will look just a very most used solution, which is Q-learning. It's very simple to use and quite immediate. And we will see each component by itself. So choosing an action in Q-learning requires solving the exploration versus exploitation dilemma. This is basically what Valeria said before. Basically, when we want to do something, we would like to do the action which minimize our future costs. So I should exploit my knowledge to do what it looks best according to my current knowledge. So I take the best action. But since I want to learn at the same time, I should also try something different, to explore, which is basically to try something different sometimes. And if you look at the theory, it tells you that if you want to convert to the optimum, which is our ultimate goal, you cannot exploit all the time, because eventually you will not learn enough. And you cannot explore all the time, otherwise you will not have the system running properly. So there are different ways to do this. A very simple approach is the epsilon greedy exploration, which is quite simple. Basically, assuming you have M action overall, you have to try them with non-zero probabilities. So the idea is that with probability 1 minus epsilon, so epsilon is assumed to be a small number, 5%, 1%, and it's quite different, complicated topic deciding the right value. I take the best action according to my current estimates of my Q function. But with small probability, I take an action at random. This is how I explore. So basically, in this case, I'm running my policy when I'm doing greedy exploration. And I have a non-null probability of doing always all the action, which is large in the case of the best action, what it looks the best action at a given moment, and a non-zero probability of doing something else. This is what I need to learn. After I observe then the state, I have to update my estimate. Then the estimate basically is a way to look at a different way of value iteration. In the value iteration, I use my knowledge of the system to update my Q function. In this setting, which is everything is unknown, basically I'm using point estimate. Basically, I have my current estimate of the Q function. I want to compute the new estimate. So I need a learning rate, which should be properly adjusted to ensure proper convergence. We cannot get into the details of this right now. Then we have the target, which means my best knowledge, which is the expected minimum cost of taking the action I just took, which is the cost I observed plus my knowledge of the best future cost that it will occur if I take the best action when I get into the future state, and take the difference with the current value. So this is what is known the temporal difference error, by the way. I use this to update my estimate, and I do this over time. So if I put the three things together, my Q-learning scaling is basically choosing a scaling action based on current estimate, and epsilon greedy works fine. Observe what happened, and then I use this to update my Q value function. And I do this over time. So I act on the system at the same time, I end up learning. Now there are two things that should be cared about, is that from one point, it is very simple. On the other point, the performance are rather sloppy. So now I'm just showing you the experiment. On the left, we're using VUI, knowing perfectly how the system will run to compute the optimal policies and act accordingly. Then in the second case, I assume I know nothing about my system and I'm just running it using Q-learning. So this is just a daily periodicity over 5 weekdays of the system running. And you can see that Q-learning takes a lot to learn, and at the very beginning, it just makes a mess. You end up experimenting all the possible level of parallelism, you end up reconfiguring the system over and over, and you end up having many performance violations. So Q-learning works, but even on a simple system, this is just a single component, homogeneous replicas, periodical, almost periodical arrival, 5 days, he has still no clue of what he should do. And this drives me to the second part, which is we have MDP using VUI, then we have Q-learning, and the two are two extremes of the same problem. One, I assume to know everything, I compute everything beforehand. Then I assume to know nothing, which is what more realistic, and I end up learning everything. Sometimes we are in between, and this is something we want to take advantage of. And this is something based on Michaela van der Schaar result on a very different topic, but it applies nonetheless to our problem. So on the MDP VUI setting, I know the probabilities, I know all the cost. And I run my system, and after solving the system. So with UI, we assume knowledge of the system dynamic and cost, and we use value iteration to compute offline our optimal policy. So I know my probabilities, my cost, and from now on, what I know, I will use sub k to indicate this is known. What is nice that when I solve IMDP, I assume I know everything. And we know that value iteration algorithm provide us the optimum. And with Q-learning, we put R in the opposite position. We assume to know nothing. Everything is unknown. We have unknown transition probability, unknown cost. And we have to deal with Q-learning, for example, to deal with our learning process. Now, the truth is something in between, because more often than not, we know something, but not everything. And we are in this ugly position. If we know everything, we can solve the MDP beforehand. But if we don't know everything, are we left with Q-learning? And the truth is something in between can be done. So assume what is the most realistic situation, which even in our simple case is actually occurring, that we have partially known dynamic and cost. So in our case, let's see. So on the top, we have the transition probabilities. On the bottom, I have the cost. In green, we have what we assume that we can reasonably know without having to do nothing really particular. In the red, what we don't know. So here we get in some detail. Let's look at the probability transition. Here tells us that when I do an action, I saw what happened to the number of replicas of my component. If I add the component and I have 3 replicas, I will end up with 4 replicas. If I do nothing, I will stay with 3 replicas. If I remove one replica, I will end up with 2 of them. But maybe on an actual system, I don't know which is the arrival rate dynamics. This is unknown. So I have partial knowledge of the transition probability, but not complete knowledge. The same on the cost. When I add the replica, which is the new number of replicas and which is how much I'm paying, unless we are dealing with variable pricing, let's assume just for instance, we are considering constant pricing, I know how much I will end up paying. If I reconfigure the system, I know I will incur a reconfiguration cost. So this is something I know for sure. If I have a violation or not, that really depends on the performance behavior of my system. And on an actual system, if the performance, which is in our simplistic scenario, the response time is very difficult to predict because it depends on a lot of things and depends on the arrival rate correlation, on the actual implementation on my code and my actual core details of the operating system and the cross effect between different components. But if I know something and I don't know something else, can I try to separate the 2 parts and take advantage of the 2 different techniques for each of them? And this is what Michele Matechar elegantly solved a few years ago. Basically, the basic idea, then we will refer to the paper for the detail, is considering the transition from the current state to the next state as two distinct transition. The first part is in a given state, if I do one action and I pay a given cost known, which is the known dynamic cost. In our case, what is known? If I do an action, I know exactly which is the next configuration. Action A is +1, 0, -1. From state K, I will go to state K plus A. I know the impact of my action on these 2 components of the cost. So non-dynamic cost, I will leave here in green. Then we have an unknown part. The unknown part is actually, after I did my action, then there is the impact of the change of arrival rate over the next interval, which I don't control. And then the performance violation I might incur on. This is the unknown part. Between the original state and the final state, I have this intermediate known as post-decision state, which is the state after the known dynamics and the known cost has taken place, but the the action, sorry, and the known dynamics has taken part, but where the known dynamic has not yet taken part. And I introduced this new state and introduced the post-decision state value function. The idea, just simply put, that I can use the value iteration type of algorithm to deal with the green part, and using the Q-learning part of the algorithm to deal with this unknown dynamic, which basically means discriminating that something is known, something is unknown, and dealing with them accordingly. If you see now that equation, this equation is exactly the value iteration type of equation, which I have the known probability and known cost to deal with, and the unknown part I deal with using something very similar to what I do in Q-learning. What is different, I don't have Q values, but rather than V values here, because I don't have any action from going from ST tilde to ST plus 1. So here, since there is no action to deal with, I can just write down the V function. And this I handle as it was in Q-learning, where I have my current estimate and update according to the unknown cost and my target cost. If I put them together, then I get what it is called a PDS learning, which basically is taking the greedy action according to the known dynamics of the system, observe the post-decision state, and after which updating according to a value iteration-like equation, the Q function of the state, and then updated the post-decision value a function according to a Q-learning type of equation. Combining the two is still very simple. I have to update two functions rather than one. In our case, it's even simpler because in our scaling action are deterministic, what happened. So these are the actual equation we implemented in the code. What is nice, this is very simple, and it performed much better than Q-learning. So this is actually what we got. And if we take the comparison with MDP, it's still quite ugly to look at it. But if we compare that with Q-learning, it's getting much better. Actually, if we look over an horizon which is much longer than this, then we can see that here they are to perform much better with very little complexity. So the message is between using VUI, which requires prior knowledge of everything, and using Q-learning, which assumes nothing about the system beforehand, we can try to blend the two approaches together and try to take advantage of what we actually know. In our system, and that go back to our scaling problem, the impact of the action is quite clear. If I'm just adjusting the number of resources or adjusting the number of replicas, which is the impact of the action of the system, is rather obvious. Q-learning assumes nothing. He has to learn what happened when I add the replica. But this is not something what we want it to learn if we can tell him directly using a combined approach. Now, since I'm already run out of time, I'll just tell you what is another option, which is rather obvious, but it ends up being costly, apart the very simple case, which is, what if I try to learn the model of the system rather than just trying to learn which is the best things to do? The idea of model-based reinforcement learning, simply put, is try to learning the model of the environment by interacting with the environment. So in our case, what does it mean? Basically, what we don't know about the system, we'll try to learn it. So what we don't know about the system, we just saw before. We don't know the transition probabilities of the arrival rate, but I can estimate that over time. I just observe the empirical frequencies and the empirical transition, and I use this to build my estimate. So I use here the at to indicate my estimate over the total running time of what the transition probability looks like between two possible arrival rate. And then I have to estimate the cost. As we saw before, the cost, we know something, but we don't know something. And what we don't know is which is the fraction of a violation I'm incurring in a given state, but I can estimate that with the empirical frequencies. And the idea, assuming on this, running the system, then I can just run the value iteration using the very update rule we see for value iteration, but using estimates of the cost, estimate of the transition probability instead of the actual values we don't have. What we end up with is a very simple conceptually algorithm, which is only an ugly part. Rather than having very couple of instructions like in PDS or one single instruction like rather in Q-learning, I can do one or multiple sweep of the entire state space to do one or more iteration of the value iteration algorithm using the current estimate. And the difference here that I have to update the estimate and update my Q values. And then I use them to decide which is the best things to do, taking the greedy action. What is nice is that in our very simple system, if we do this, we get very good performance compared to the MDP, just because this is a very easy system with very periodical non-variable input. So in this very simplistic case, I can spend a lot of time doing value iteration while the system is running, but I get very good performance without having to learn very slowly. This is what happened with AQ learning. So a final comparison and why we had discussed the different topics is because in the simulation, we were just looking at 4 or 5 days. This is over an entire year, assuming this type of regular input. We have the VUI solution, which is our optimal. So this is why we need to introduce the MDP, because we want a benchmark of what is the optimal behavior. And Q-learning tell us that it works, but it learns very, very, very slowly. Even after 1 year, its performance is rather bad, 50% worse than the optimal. Q-learning with post-decision state, which means take advantage of what I know, is not very good, but performs much better with very little additional cost. If I run a value iteration step every time step, I can do much better because I learn basically how the model is and I get almost optimal performance. This shows us that there is a trade-off between computational cost at each iteration and which depends on how big the state space, how big the problem is, and the actual performance. Why we care about this? Because in our setting, we have apps. We don't have just single components where everything was easy to deal with. The performance requirements scale to the entire application. So I might be interested to the maximum latency. And the idea, I have a global component that oversees the entire application. In this case, I can just replicate what I just told you, just changing the model. And the model is basically a vector, which is the state, the replication level of every component in the system, and the arrival rate at each component. And the action state, the action space is what I do component per component each action. And this is something that we can deal with what we just showed before, but the MDP is almost impossible to solve. I don't have all this information on the running system. Q-learning behaves very poorly, even in a simple scenario, not to mention what I would expect in this setting. And learning using value iteration step by step using estimates requires a lot of computation because now the state is exponential on our system. So from now on, we will deal how we can address this problem even for simple application with few nodes using technique which leverage on function approximation on our Q function and action value function. So if there are not many questions, I leave the stage to Gabriele, who also put together a simple simulating experiment to try to let you play around with happen when you change and use different configuration for a simple one component a simulator and see with different learning output how it behaves. But I leave him the pleasure to show you how it works, and then after, I guess, another 5 minutes break, get to the third part of the talk. Thank you very much. I apologize for my rusty English, which I've been tested for a while, and thank you very much for attending. That's it, if there are no questions. Yeah, I mean, I guess that's...
So, hello everyone, I'm Gabriele. Now we have a 5-minute break. If you want, you can try this very simple simulator. You can just browse this URL you see on the slide, and you'll find a very simple web application that hopefully will work. And so we will resume in 5 minutes. And if you have any questions about the simulator, I'll be available. So just post a message using the chat box. Then final part of this tutorial. And in this part, we'll discuss how to deal with large state spaces. And in particular, we'll discuss value function approximation. So far, we have considered so-called tabular representations of the value function. So we have assumed to rely on a lookup table, which allows us to store and update the value of any state and action at any time. This approach is easy to analyze and implement, but unfortunately, it is not ideal, especially as the state space grows, for various reasons. First of all, the memory demand of such table grows proportional with the size of the state space. So we could have some scalability issues. The second problem is using this kind of representation of the value function, we don't have any generalization. Because every time we learn something and we update the value of a single state, this update doesn't impact any other state in our model. So the new knowledge doesn't propagate automatically to any other state. And the third problem with this representation is that it cannot handle continuous state spaces, because of course, in the table, we need to have countable states. So to see an example where we start having problems with the size of the state space, let's extend a little bit the autoscaling use case we have considered so far. So now we consider a heterogeneous computing infrastructure in which we have computing nodes with different types or amounts of computing resources. So just think of virtual machines in the cloud, where you can have small, medium, large instances. And of course, you have a trade-off between cost, computational capacity, energy consumption of the different machines. In this case, we don't only have to decide how many replicas to run for each application component, but also which type of nodes to use for hosting them. So the problem becomes clearly more complex. We can revise our MDP formulation that we have seen in the previous part to consider this resource heterogeneity. In particular, we can consider to have n different types of computing nodes. In this case, we need to extend the state of our application component. So in the previous examples, we had a scalar value key which denote the number of replicas of our component. Now we need to use a vector key where each component of this vector denotes the number of replicas that we have on a certain type of computing node. And then in the state, we have also lambda, as we had in the basic example, which denotes the application input rate, so the current workload. We also need to extend the set of the actions we have in the new MDP, because now we still have scale in, scale out, and do nothing actions. But when we decide to add or remove a replica, we also need to specify the type of node where we want to add or remove the replica. So the state space becomes more complex, and so does the action set. As regards the cost function we use in this example, it is almost identical to the one we used before. The only remarkable difference is that when we evaluate the resource usage cost, we need to take into account the specific cost for each different type of computing node that we can use. The other terms, that are the reconfiguration overhead and the performance violation penalty, remains unchanged. Now, how much memory do we need to store the Q table, so the Q function for this kind of MDP? You can see that as the number of different node types that we have in the model grows, the memory required by the Q table explodes. So if we have more than 5 different types of computing nodes, we need more than 1 GB of memory just for the Q table. And we must keep in mind that we are assuming that we are controlling the auto-scaling for single application components, being them microservices or something else. And each component has its own policy, and we will need a Q table for each of them. So clearly, this kind of approach doesn't scale if we need to store tens of gigabytes of memory for each component just to control auto-scaling. So there are different techniques in the literature to deal with state space explosion in the context of reinforcement learning. We will discuss just one of them, that's value function approximation. The idea here is to resort to parametric function approximation and to replace the value functions V and Q with an approximate version that's a parametric function which depends on a vector of parameters W. The size of the length of this vector of parameters is denoted by D, and we usually expect D to be much smaller than the number of states in the model. So now we don't need to store the whole Q table, but we only need to store and update the vector of parameters. This clearly leads to significant memory savings, but also to potential generalization across different states, because when we update a single weight in W, we are likely to impact the value of several states. There are some questions we have to answer before being able to apply this technique. The first one is how to pick a function Q hat or V hat for approximating the value function. And the second one is how to compute the parameters W to approximate the true value function. So it's useful to formalize the problem a little bit. First of all, we need to define what it means for us to approximate the value function. And a natural choice is to minimize the mean squared error that we have with the approximate version of the value function summed over all the states in the model. And what we can do then is to apply gradient descent to update the weights so as to minimize the mean squared error. So what we do is we compute the gradient of the loss function, and we move in the opposite direction of the gradient using a step size alpha. Now, this rule is pretty simple, but we have some problems when trying to apply it. The first problem is that to compute the gradient, we need to compute the summation over all the states in the model. Unfortunately, this can be quite expensive on a computational point of view, so we want to avoid this summation, and we can resort to stochastic gradient descent, where we just compute one or few samples of the value function at each step. So we don't have anymore the summation, and we can just focus on a single state at each step, and we compute the approximation error for that specific state. The second problem we have is that the formula requires us to know the exact values of the value function to compute the error. But unfortunately, we don't know the value function. Otherwise, we wouldn't need to learn it. So what we perform in practice is a semi-gradient descent, because we replace the true value function with some noisy approximation of it that I denote as U. And the different algorithms that we can use differ in how they compute this noisy approximation of the value function. But overall, we end up with a very simple update rule to compute the parameters W. Now, as regards the choice of the function to use for the approximation, the simplest approach we can consider is linear function approximation, where the approximate function is a linear combination of the weights W and a vector of features. The features are functions that associate states with some real values, and these features are used to capture some properties of the states. So, for example, a feature of a state in our autoscaling example may be the normalized parallelism level in a state. When we consider linear function approximation, the update rule for the weights W becomes very simple, because if we get the derivative of V hat, we just end up with the features themselves. And when we replace this term in the update rule, we end up with a very simple update rule. Clearly, we can write down equivalent formulas for the Q function. The only difference is that now we need to capture relevant properties of both states and actions. So we have features that depend both on S and A, but the update rule we end up with is almost identical. So the last question we have to answer is how to compute such approximation of the true value function that we can use in the error computation to update the weights. So the algorithm we consider is an extended version of Q-learning, where we integrate the linear function approximation. So it's useful to recall the basic update rule of Q-learning that you have seen in the previous part of the tutorial. And we can know that in the Q-learning update rule, we compute the error based just on the immediate cost that we observe online. And in order to estimate the future costs that we may incur from that point onwards, we just rely on the estimates that we have of the Q function. So we can use the same approach in this extended version of Q-learning, where we compute the noisy approximation U, summing the observed cost C that we observe at each step, plus gamma that multiplies the estimates that we have of the future cost based on the current estimate Q hat. So we use the same approach we used for plain Q-learning, but this time we use the approximating function Q hat. And then, instead of updating an entry of the Q table, we update the parameters W using the formula we have derived in the previous slide. Okay, so this allows us to compute the weights online and to improve our approximation of the value function. The model depends on the features we use to represent states and action in our model. And clearly, the accuracy we achieve depends on how well states and action are represented by the features, as in almost every machine learning problem you can think of. So the features should capture relevant properties of the states, and clearly they are domain specific. And we also must always keep in mind that we expect to have a small number of features, because otherwise we may lose all the benefits that we have on a scalability point of view. Just to give you an example, we can note that tabular reinforcement learning can be regarded as a special case of linear function approximation, where we use exactly one feature for every state in the model. Each feature is a binary function, which is non-zero only for a single state. If we compute the weights using these features, we end up having a parameter W, I, which corresponds to the value of the state I. So in this case, we may have an approximate function V that is identical to the true value function. But of course, in this scenario, we have no memory savings because we are using exactly one feature and then one parameter for each state in the system. So there is no advantage in doing so. So designing features is often a complex problem because we need to use domain expertise to handcraft features. There are some techniques that provide us some guidelines for feature definition. So for example, we can exploit tile coding. According to this technique, the idea is to partition the state space with tiles. So tiles cover a region of the state space, so they cover multiple states. Each tile is associated with a binary feature, which is activated, so it's non-zero, for states that are covered by the tile. So the idea is that we can generalize over contiguous regions of the state space because each tile aggregates multiple states. And if we consider different shapes, size, and layers for these tiles, we can define a set of features in a semi-automated way. So for example, in a work of ours, we define some features for the auto-scaling problem that we have presented before using tile coding, and in particular aggregating states along 3 dimensions that are the input rate in the state, the overall application parallelism in the state, and the set of used resource types in the state. We consider 2 tiling configurations. In the first one, we used all rectangular shaped tiles, while in the second one, on one surface of this 3-dimensional tiling, we consider diagonal stripes that aggregate states where the input rate per replica is similar. So states that have a similar utilization level. Now, there is just a final issue, is that to approximate the Q function, which depends both on states and action, we need to represent both states and action, not just states. So we need features which depends both on states and actions. Tile coding provides us a strategy to aggregate states. What about actions? So a simple approach is to define the features for the states and then replicate those features for every action. So we have a set of actions, we have a set of features, and we replicate them for every action. So depending on the specific action we are interested in, we activate a specific portion of our feature vectors. Clearly, this is not ideal because the number of features quickly grows and we don't like it. So we can end up with a smarter approach if we can again resort to post-decision states. To do so, we need to recall what we aim to approximate. We aim to approximate the Q function, which gives us the expected discounted total cost starting with a certain state and action. This discounted long-term cost can be seen as the sum of all the immediate costs that we pay at each time step. And we can also recall that the immediate cost is computed as the weighted sum of 3 different terms, which accounts for different types of costs. So the resource usage cost, the performance violation cost, the reconfiguration cost. If we reason on this cost, we can note that actually the resource usage cost doesn't depend on the specific action we have performed once we are in the post-decision state. So once we have computed the new application configuration, we can forget about the specific action we have performed. Similarly, the performance violation that we may have at any time does not depend on the specific action we have performed once we have the post-decision state, which describes the new configuration in which the application runs. Differently, the reconfiguration cost depends on the action we perform, because if we perform a scaling operation, we pay some reconfiguration penalty. Conversely, it does not depend on the specific state where we perform a reconfiguration. So we can divide the different costs into 2 groups. Some costs are related to the post-decision state in which we are, while other costs depend on the action we perform. So we can imagine that the approximate Q function we want to compute is made up of 2 different terms. One depends on the post-decision state and one depends on the action. So the problem of defining features can be divided into 2 sub-problems. One problem consists in defining features for states that are post-decision states actually, while the second sub-problem consists in defining features for actions only. And the approach we can consider for our autoscaling example consists in using tile coding for the definition of state features, while for the action-specific features, one single feature is enough, because we just need to distinguish reconfigurations from do-nothing actions. So we can just use one single feature to solve the problem. But in this way, we have divided the problem into 2 sub-problems that we can solve. So at the end of the day, how much memory do we save using linear function approximation? You can see that compared to the tabular reinforcement learning case, the memory savings are significant. We can easily handle the scenario where we have 10 different types of nodes with less than 10 megabytes of memory. And if we look at the average cost we achieve in a simulated environment using the tabular Q-learning, the Q-learning with functional approximation, and the value iteration algorithm with and without functional approximation, we can see that in the case of Q-learning, the performance is dramatically improved when we use functional approximation. And if we solve the MDP with and without functional approximation, we cannot note any difference. So with functional approximation, we have dramatically reduced the amount of memory we need, and we have also improved the accuracy of Q-learning. So linear functional approximation is attractive because it gives us a very simple model to update and analyze, but it also has some drawbacks because, as you have noticed, we need to put a lot of effort in the definition of features in order to achieve a good accuracy. So a natural upgrade we can consider is moving to nonlinear functional approximation. So to consider more complex functions for our approximation. And of course, we can especially think of artificial neural networks, since they have been applied to a large number of different problems and domains. You probably know what an artificial neural network is better than I do, but just to say a few words, an artificial neural network is a collection of units called artificial neurons. Neurons are connected to each other, and with each connection, we have associated a weight. Each neuron in the network uses an activation function that is a nonlinear function of its inputs to produce an output, which is a real value. And in the network, the output of each neuron is used as the input for neurons that are in the next layers of this network. So in the network, we have an input layer which contains the input values that we give to the network. Then we have some hidden layers which comprise neurons. And then we have a final layer that is called output layer, which produces the output of the network that we can see. By training the network with some examples of the expected outputs we want for some inputs, we can somehow teach the network how to approximate very complex functions. And we want to exploit such approximation ability of the artificial neural networks, while we also want to have the network take the burden of constructing features for our problem. So we want to relieve the user from this burden of handcrafting features. So for this purpose, deep neural networks are especially useful. Deep neural networks are basically neural networks where you have multiple hidden layers. And in this kind of networks, each layer possibly computes a new representation of the input of the network. So it is able to learn which is the best representation of the data to use for the approximation. And this is something we like. So when we want to apply deep neural networks to the reinforcement learning framework, what we use is a so-called deep Q network, which is a network in which the input consists in a state, possibly with proper encoding, and the output layer comprises one element for every action we have in the model. So basically, each element of the output of the network corresponds to the current estimates that we have for the Q value of the input state and an action. When we train a neural network, we usually rely on a training dataset. So we have a large collection of examples of outputs and inputs of the network that the network can use to learn from. In our case, we will need to have pairs in which we have a state and the expected output, that is the true value function associated with that state. Then we can pick from the literature algorithms for gradient computation, for example, backpropagation, and parameters optimization, for example, stochastic gradient descent. We may use specialized hardware for efficient training, for instance, GPUs and TPUs, and we may want to pay attention to many more issues, such as avoiding overfitting, possibly vanishing gradients, and so on. So these kind of issues are out of the scope of this tutorial, but in general, we can think of having a training dataset and being able to train the network with those data. The problem is that actually we don't have the true examples of the value function to use for training. This is the same problem we had for linear function approximation. So what we need to do is to estimate Q online based on experience, as usual in reinforcement learning. To do so, we need to introduce a new concept, that is the experience replay. So the idea is that we want to perform training iterations of the network using mini batches of experience. When I talk about experience, I mean all the information that we can collect during system execution. So we can keep track of the state we enter, the actions we perform, the states to which we transition, the costs we pay. All this information can be stored in a buffer that we call experience buffer. And when we want to perform a training iteration, we can replay this experience. So a naive approach would consist in defining a size for this mini batch, let's say B, and using a buffer of size B. So what happens is that we, at each iteration, we train on the most recent experience we have in the buffer at that moment. There are some problems with this approach. First of all, if we use sequential observations for training, these observations are likely correlated, and this can lead to convergence problems. The other problem is that if we also always use the most recent experience, the network may forget about what we saw in the past. So we need a smarter approach. And the smarter approach consists in having a buffer, an experience buffer that is larger than the mini batch we want to use for training. So what we do at each step, we draw randomly a mini batch of experience from the buffer. In this way, we are going to reduce or remove the correlation that exists between sequential observations. Moreover, if the buffer is large enough, we are likely to replay all the observation more than once. So the network is likely not to forget what it observed in the past. With all these building blocks, now we are able to define a new version of the Q-learning algorithm, which is deep Q-learning. Basically, this is Q-learning where we use a deep neural network, or in general, an artificial neural network, to approximate the Q function. The general scheme of this algorithm is similar to the basic version of Q-learning. At each step, we pick an action, for example, using epsilon grady action selection, and then we gather some experience. So we observe a transition to a next state, and we observe a cost. Now, the difference that is we don't use this experience immediately to update the Q function, but we store it in our experience buffer. Then, in the update phase of the algorithm, we sample a mini batch of experience tuples from the buffer, and we use this mini batch to update the network. So at this time, we need to compute some targets for the update. So that is, we need to compute the values y that are the expected output of the network given a certain state in input. And to do so, use the formula that we have used so far for Q-learning that only depends on the observed immediate cost. So we sum the immediate cost C with the estimated future cost that comes from the network itself. So we use the network to estimate the future cost. And then when we have prepared this mini batch, we can perform an iteration of, for example, gradient descent to update the network parameters. There may be a problem with this approach because we are using the network output to compute the update targets, as I mentioned. And the thing is that we train the network using this targets value, which depends on the network parameters W, and we keep changing W at each iteration. And this can lead to instability during training. So a solution that you can easily find in the literature is the use of the target network. So we use a second neural network during training to stabilize the targets. So if we consider this extended version of the algorithm, we see that we keep two versions of the parameters W. So basically we have two neural networks. When we need to compute the update targets, we estimate the future cost using the target network. And when we need to update the parameters W, we don't modify the target network. Only periodically, every 6 steps, we update the target network with the most recent version of the parameters W. We may further extend the deep learning algorithm, introducing again the concept of post-decision state, because we may ask ourselves whether we can exploit post-decision states to achieve faster convergence. So we want to take the best of both the worlds. So we want to use the partial information we have about the model to speed up the learning process. But at the same time, we want to use deep neural networks to reduce the memory demand of the algorithm. To do so, we need to slightly revise our network architecture, because in this case, we want to approximate the PDS value function V. So the new network takes a PDS in input. So it is still a state, but now it represents a post-decision state. The main difference regards the output of the network, which now comprises a single element. That's the estimated PDS value function. Then defining the extended version of the algorithm is straightforward, because we just need to modify a few lines in the algorithm. First of all, we need to recall that when we know the PDS value function, or as in this case, we are able to approximate the PDS value function, we can easily retrieve the Q function by summing it with the known cost. Then at line 6, we can replace epsilon greedy action selection with a simple greedy action selection. Then at line 7, there is probably the main difference in this new version of the algorithm. When we store a new experience tuple in the buffer, we don't need to store the observed cost as it is, but we only need to store the unknown cost that we have observed at this time step. And to compute the unknown cost, we just subtract the known cost from the observed cost. And then we use this new, we construct mini batches for training using these experience tuples, and we perform network training as in the previous example. A final issue regards how to give states in input to the network. So in principle, deep neural networks are able to learn representations of the input data at each layer. So we could forget about feature engineering in this case. It is true, but actually using some features is still useful, because if we manage to define a better representation of our states, we can likely use a less complex network or probably speed up the convergence of the learning process. So the most simple thing we can do is just to connect each component of the state vector to an element of the input layer of the network. Probably we just want to normalize each state component, because we know that neural networks works well if it has normalized inputs. So in the autoscaling example, we may just connect each element of the vector key and lambda to one input element of the network. An opposite strategy may consist in using one-hot coding both for key and lambda. One-hot coding means that we associate each possible configuration of the state with exactly one input element that is non-zero just for that specific state configuration. But in this case, of course, we have a very large number of input elements, which grows exponentially with the number of computing nodes that we have in the model. So in between, we may have alternative encodings of the states. For instance, we may use one-hot coding for each different component of the vector key. So we may encode each component of key independently from the others. And for lambda, we may either normalize lambda using a single input component, or we could rely on one-hot coding for lambda. But the advantage of this kind of representation is that it doesn't require an exponential number of input elements when the number of computing nodes grows. And if we look at the memory demand that we have using these different strategies for encoding states, we can see that if we use the large state encoding, we end up having requiring more memory than the Qtable would do. So that kind of encoding is not good, clearly. But all the other strategies have presented lead to significant memory savings compared to the tabular approach. So we can easily handle 10 different kind of computing nodes with few megabytes of memory. That's what we expect. And if we look at the accuracy we can achieve using deep Q-learning, in this case, you see on the left, baseline results using Q-learning with post-decisional states and the optimal value iteration. On the right-hand side, you see what happens using Q-learning with function approximation and deep Q-learning with post-decisional state. All the algorithms on the right-hand side perform much better than traditional plain Q-learning, but we can note that especially algorithms where we use the post-decision state perform very well. They are very close to the optimal average cost of value iteration. And it is worth noting that the PDS can be either used explicitly in the algorithm, like we do in deep Q-learning with post-decision state, or indirectly used in the feature construction, as we did for Q-learning with linear function approximation. Another example we can consider is what happens if there is something that is non-stationary in our environment. So for instance, what happens if the application workload suddenly changes at some point? So in this simulation, we suddenly modify the application workload after the first half of the simulation. And what's interesting here is that dynamic programming approaches like value iteration are not able to adapt to this kind of changes. So you see the cost associated with dynamic programming significantly grows when the workload changes. Conversely, reinforcement learning algorithms are able to adapt to changes and learn a new policy. So they are not significantly impacted by this change. So we are reaching the conclusion. We must keep in mind that our ultimate goal is not to control single components in the application, but the whole application. As Francesco mentioned before, we usually have performance requirements expressed for the whole application. For instance, we may have maximum response time requirements for end-to-end path in this application graph. And our approach is to have a global controller oversee the overall adaptation. To do so, a possible approach is to let this global controller tune the cost function of the local controllers. Tuning the cost function means tuning the weights associated with the different cost terms, and most importantly, defining a suitable performance requirement for each component based on the overall requirement for the application. And to do so, we have considered different techniques. For instance, you may rely on some model-based heuristics, for instance, relying on an approximate performance model of the different components, or you can use some black box optimization techniques to simulate the behavior of the local controllers and identify the best configurations of their objectives that leads to the best performance for the whole application. So, to conclude, here you can find some essential references that cover the topics we have discussed today. In particular, you have some excellent books by Sutton and Barto and Bersekas, and also a course on reinforcement learning by David Silver that is provided and made available by DeepMind. You also may find some more specific references on specific topics like linear function approximation and deep reinforcement learning. If you're interested in these topics and you want to experiment with reinforcement learning, there are several open source software libraries that you can use and you can use to avoid implementing the basic algorithms from scratch. Just to name a few, you may use OpenAI baselines, TensorFlow agents, Keras reinforcement learning 2, and you may even find more of them just searching on the web. So to draw some conclusions, in this tutorial we have seen that uncertainty can play an important role in runtime system management. Reinforcement learning provides a rich toolbox to learn control policies for complex tasks. And in particular, we have seen that if we blend together models and learning agents, we are able to learn from fewer data and in a reduced amount of time. When we have to deal with very large state spaces or continuous state space, we can resort to function approximation techniques and in particular deep reinforcement learning to avoid scalability issues. What we have seen today in this tutorial is just the most simple material you may find on reinforcement learning, because there are several more advanced topics that we haven't discussed today. I want to point out some of them in case you are interested. For example, value function approximation is not the only approach to deal with state space explosion. There are a lot of techniques that rely on so-called policy gradient methods, in which you basically don't need to search for the optimal value function to identify the optimal policy, but you directly search in the policy space. And then there is the actor critic framework, which has been successfully applied to many problems, in which you combine both the approaches. You search in the policy space and in the value function space. Then, if you have multiple components in your system that make decisions at runtime, what you end up with is a multi-agent reinforcement learning task in which you have several agents that work in the same environment in either a cooperative or competitive setting. In this case, you don't anymore work with a Markov decision process, but what you have is a Markov game. So you probably, in this case, need to settle for an equilibrium policy. And you have a lot of new problems to solve. When you have very complex tasks to solve, you may resort to hierarchical reinforcement learning, which revolves around the idea of decomposing a complex task into subtasks. So an agent can resort to a sort of subroutines to solve particular subproblems that may arise during execution. Also, to deal with state space explosion, you may combine reinforcement learning and tree search techniques, in which you try to learn the optimal policy for the whole problem, for the whole model, but when you need to pick an action, you also perform a local search around the state you are in a given moment. And as in all the machine learning areas, we are also interested in transfer learning, because when we learn a policy to solve some task, we would like to be able to apply the knowledge we have acquired to a new and different task. So here you can find some minimal references to works dealing with these topics. And from my side, it's all. If you have questions, we are available to answer them now. At the end of the slides, you'll find a long list of references on the different topics we have discussed today. And I think the slides will be made available using the conference website soon. And so I want to thank everyone for the attention.
Thanks a lot. Thanks a lot to the three speakers, actually, to Valeria, Francesco, and Gabriele for the very nice tutorial. I think there were a lot of suggestions and interesting topics. So I think that maybe that the discussion can continue also on Slack channel and then also offline, I guess.
Yes, we'll be also available to answer questions offline.
Okay, so thanks a lot, and thanks a lot also to everybody for attending.
Thank you.
And, yeah, thanks a lot also from my side. I mean, I was in the other tutorial, managing the other tutorial. I will watch your recording for sure, because I'm really interested in the topics you covered today. And I think are a really hot topic. I mean, there is a lot of interest also at the European level. European Commission is really pushing the option of reinforcement learning and AI in general for managing the cloud infrastructure we have been working in the last years, actually. So really thanks to you, thanks to Valeria and Francesco, and yeah, hope to see you the next days during the conference.
Thank you.
Thank you.
Bye.
Bye bye.
Bye. Thank you. Bye. Bye. Ciao.
Bye.